Well, let's briefly discuss moment of inertia of hollow sections. Nothing really special here from my mathematical or computational point of view, but conceptually it's really important to understand these. So first of all, the moment of inertia would simply be the moment of inertia of the outer figure minus the moment of inertia of the cutouts. So if you had something like this or something like this, which are called pipes, right? You will basically compute the moment of inertia of this outer figure and subtract the moment of inertia of the cutout. And if they are both concentric, then it's really easy, right? It's simply 1 over 12 b outer h outer cubed minus 1 over 12 b inner h inner cubed. And that's it. There is nothing to it. Same thing you can do with this. Again, if this circle is concentric with the centroid of the triangle, you can do a simple subtraction. Same thing with this type of section where you may have a rectangle with two circular cutouts. So nothing to it. So long as they are concentric, it's no big deal. You can use the regular formulas. If they are not concentric, then you have to use parallel axis theorem in order to further subtract the effect of the whole being off-centered. But that's trivial, right? The real insight here is to understand that these sections have tremendous efficiency because, again, as you remember from the definition of moment of inertia, the key here is y squared. So if most of your area is far away from the centroid, this will add up really quickly. So the area that really matters is the one that's on the perimeter. This area here near the centroid contributes very little to moment of inertia, but it adds to the self-weight and it adds to the cost of building that element. And so if you can subtract area from a location where it doesn't contribute much to the moment of inertia and just keep the one that contributes the most, that is a very, very efficient structural shape. And again, these are extremely efficient. You also have the case of I-beams, which would basically be a rectangular cross-section from which you subtract two other rectangles, and then you end up with this really efficient type of shape, which is what we call an I-beam. And so this subtraction theorem is really useful and enables the computation of very efficient structural cross-sectional shapes.